Okay, so welcome everyone to attend our second seminar of IEEE ComSoc SPS ISAC webinar series. And this is our second season. And so today we have two guest speakers, Professor Christos Masouros from University College London and Professor Wei Yu from the University of Toronto. And so before we begin the presentation, I would like to advertise a bit about our recent call for papers of two special issues of our ISAC ETI. One is actually on a special issue on integrated sensing and communications for future green networks on actually TGCN, so transactions on green communications and networking. And the submission deadline will be the 15th of June of this year. And the next couple of paper is on actually Open Journal of Communication Society, which is also focusing on ISAC for multifunctional networks in 6G era. And the deadline will be May the 15th of this year. Okay. So I would like to give a brief introduction to our first speaker, Professor Christos Masouros, and who has been my postdoc supervisor and a very good friend. So I knew Christos since I think 2016, and so Christos is now a full professor at University College London and working in signal processing and wireless communications. So his research interests lie in the field, in particular on green communications, large-scale antenna systems, and of course, integrated sensing and communications and interference mitigation techniques for MIMO and multi-carrier communications. And he has received numerous best paper awards, including the IEEE SPS Young Author Best Paper Award. And the best paper awards are from Globecom and WCNC, and has been recognized as exemplary editor and exemplary reviewer for several IEEE transactions and journals. And he is an editor for IEEE TCOM, IEEE TWC, IEEE OJSP, and editor at large for IEEE OJCOMS. And he was an associate editor for IEEE Communication Matters. And he has acted as a guest editor for a number of special issues on IEEE GSAC and IEEE GSTSP. And he is a founding member and vice chair of our IEEE ISAC ETI. And he's also the vice chair of IEEE SIG on ISAC and chair of the IEEE SIG on energy harvesting communication networks. So before we begin our presentation, I would like to remind you again that during the seminar, our audiences will be muted, and please do not annotate on your screen. Please type your questions and send them to host or co-host, so me or Yuanhao, and we will collect all the questions from audiences from Zoom and offsite live broadcasting. And during the Q&A, we'll choose 3 to 5 questions, and you will be named, and you are encouraged to ask questions by yourselves. Okay, so that'll be all for my introduction. And so Christos, we will all look forward to your wonderful presentation.
Great, thanks a lot, Fan. Let me start by sharing my screen.
Yeah, I'll stop sharing.
Okay.
Yeah.
So. I hope you guys can see this.
Yeah, perfect.
Okay, great. So thanks a lot, Fan, for the introduction, and thanks a lot to the whole ATI for inviting me to give this talk. It's always a pleasure to talk about integrated sensing and communications. So what I'll be talking about is this very topic. I'd like to give some extensions related to security, which I think are unique for this topic. But also some broader, discussion on signaling and waveform design for the integrated communication and sensing. I have to say, as Fan mentioned, he was in my group for some time, and a lot of this work actually has been led by Fan and his colleagues in my group. So I'd like to acknowledge them for their work in this. Just to start off with a bit of motivation, to my observation, this area of integrated sensing and communications has started by the observation that, radar and communication systems are seeing an increasing cohabitation of common frequency bands. So low gigahertz bands that are traditionally used for air traffic control radars and big radars, surveillance radars, and so on, have seen increasing use from commercial communication systems such as 4G LTE and now 5G New Radio. But also this is expected to expand in the millimeter wave bands, where smaller radars such as automotive radars will be coexisting with new frequency bands of 5G radios. So the classical approach to addressing this coexistence has been spectrum sharing techniques between radar and communications, borrowing ideas from communications system spectral coexistence. And the main limitation here is interference and the need to address interference. So you have interference from the communication transmission to the radar receiver when it's receiving its echoes, and from the radar transmitter to the communication receivers. And here's an elementary example. So dealing with this interference requires synchronization, requires these two different systems to coordinate. It can include overheads in the transmission. And it's also a bit risky when you have radar critical applications where you cannot tolerate any communication interference. You cannot tolerate errors, let's say, in the coordination, or communication critical operations, again, where you cannot tolerate any interference. So it has its limitations. And there's other, motivating factors that, the coexistence alone does not really address. So challenges include, for example, having this growing population of sensors and transceivers for communications and sensing. And here's an example from let's say, civilian applications. So this is a classical field where this applies, so connected vehicles. So connected vehicles will be expected to communicate with different means of communications, vehicle to vehicle, vehicle to infrastructure, vehicle to pedestrian, vehicle to device, and so on. And at the same time, they're equipped with a number of sensors, including cameras and LiDAR, but also a number of different radars, long, medium, and short range radars for different applications. So cruise control, traffic alert, anti-collision alert, pre-crash, parking assistance, and quite a few others. So there's this growing population of sensors in the connected vehicle technology, and there is definitely scope in trying to make this a little bit more sustainable and trying to merge different communication and sensing devices. We've seen this highlighted a lot also in the military domain, where the complaint there is there's too many RF systems and the numbers are growing and the sizes are growing. So you have RF systems for communications, friendly communications, or enemy jamming, enemy intercept, also sensing attacks, sensing threats, sensing and mapping the environment, and quite a few others. So different types of communications and sensing functionalities, different types of platforms. And as you tend to increase the requirements from these platforms, the performance requirements, these platforms tend to increase in size, in weight, in area, and so on. So having all these platforms growing at the same time is not really sustainable. So there's been a drive to explore whether these radar and communication systems, the separate platforms, could be merged. And that's where this concept of dual functional radar and communication system comes in. So I see it as a step change from the classical comms radar coexistence. So where before you had the communication and radar systems competing for the same resources, frequency, power, and so on, now you have one device doing two things. So doing both communications and sensing with a single bit of hardware, a common infrastructure, and a single signaling, right? So one waveform, one signal that at the same time communicates to a number of users, while at the same time the same waveform is good for detecting or tracking different targets. There's obvious benefits in terms of making this business, let's say, more hardware efficient, more power efficient. Now you have one device doing both things. So there's one device consuming power. is also cost efficient. And going beyond these, you can now make these this operation by having the operation coming from the same device. You can make it mutually benefit both the functionalities, the radar functionality and the communication functionality. And if we think on let's say a system level, and if we imagine now with the expansion of 5G base stations and the dense deployment of base stations, small base stations being deployed on street furniture like lampposts, walls, sides of buildings, and so on. And if you can now assume these base stations being dual functional, then you have a communication or wireless infrastructure that's no longer just doing wireless communications, but also sensing and smart city applications, such as incident detection that you have here, monitoring, security, critical infrastructures, urban security and threats detection, and many others. And there's this opportunity through the communication infrastructure to make radar a commodity. So not just anymore the big radars, the power-hungry consuming radars, but radar and sensing functionalities through the communication infrastructure. So just to outline a number of gains that we see in this technology. Obviously, as I mentioned, there's this hardware gain where before you had two separate systems. So a communication system and a radar system. Now you have, let's say, a super, let's say, access point that can do both things at the same time. Obviously, that has, as I mentioned, savings in power, savings in hardware complexity, and so on. There's also this spectrum gain, which is in line with the coexistence scenarios, where before you had separate spectra for radar and for communications, coexisting with a million other applications. Now you can have, through a single transmission, both of them coexisting in the same frequency, in the same resources, and make space for other applications that are frequency or spectrum demanding. Beyond, however, these, once you now co-design these two systems, the communications and the sensing system, you can design flexible trade-offs between them. So you can design a system, an access point that goes all the way from full radar centric applications, so full radar performance, to full communication performance, and all the way in between. And going beyond, you can come up with new synergies between radar and communications, which are difficult to implement when these systems are separate. So sensing assisted communications, and we'll see an example later on, and communication assisted sensing. And also I'll try to highlight the importance of having these synergies between sensing, communications, and security, both communication security and sensing security. In terms of signaling, we typically classify the dual functional radar and communication signaling technologies into three main categories. We have the radar-centric design, where the basic principle is shown here. You take basically a radar waveform, a known radar waveform that is well designed to do a radar task, and you try to modulate information on top of that waveform. And that will give you a radar-centric approach where hopefully the radar functionality remains unchanged or has very small, let's say, penalties, while you're able to convey information through this radar waveform. And there's a number of works in the area, starting from pulse interval modulation, which we now think was the first, let's say, approach ever in history in the 1960s to try to merge radar and communication transmission, but also modulating information in the side lobes of the radar beam pattern or other general index modulation approaches. And I will be showing some recent results we have in this area. A second approach is this communication-centric design, so the reciprocal approach, where you take a communication waveform, a waveform that's designed for communications, OFDM, and so on, and you try to use that for radar detection. So use the same waveform as your reference waveform and apply classical radar processing to extract information about targets, detect targets, or track the parameters of targets. And there are actually some communications waveforms, such as the pilot signaling and the preambles in the frames, which are very well suited for radar processing. So these two categories are, the benefit of these are that you make minimal changes to classical signaling and waveforms, either the radar communications. So they would be, let's say, more suitable to apply, let's say, immediately and more standards relevant. But they have a limitation in the sense that the radar waveform is not designed for communications, for signaling exchange. The communication waveform is not designed for radar detection. So they have limitations. They're difficult. The performance is difficult to tune. The waveforms are difficult to make explicit trade-offs between the two functionalities. And that's where this new, the third category of design comes in. So jointly optimized design, where, as I said, you design a new waveform from the start so that it's good for both radar and communications, so that it can provide you with a flexible trade-off between radar and communications, so that it can provide you the high rates that you need for communications and also the reliability you need for radar detection. And that will be basically the main focus of my discussion today. So having done with the motivation, I'll try, time allowing, to basically highlight a number of technical advances that come from our group here in UCL. So I'll start with overviewing some research experiments on a radar-centric based DFRC design. Then I'll move on to this joint DFRC design that I mentioned, and I'll show an example how this can be done through weighted optimization. Also, I'll show how this can be expanded to make hardware efficient DFRC waveforms and signaling. And then I'd like to highlight the issues of security for DFRC, which I think are unique, and a couple of solutions that are tailored to DFRC systems. I'll finish off with more like a use case of DFRC in an sensing assisted communication scenario, where basically the sensing assists the establishment of a communication link in a high mobility scenario. And I think this well links with what I understand Wei is going to talk about later on. So first of all, the radar-centric design. So our radar-centric design, the recent study has been trying to apply this in the lab and doing some experiments and basically convincing ourselves that this can be done over the air. And we've taken an approach based on index modulation. Probably the best place to read about index modulation for comms radar is this paper over here, 2 years old by now, where a DFRC approach is taken using a MIMO radar, so multi-antenna radar, an FIR radar, and information is modulated on the indices of the antennas that are transmitting and on the frequencies that are transmitting. So having a combination of different frequencies and different antennas to transmit from, so here's an example of 2 antennas and 4 frequencies, that gives you the size of your constellation. So if this example gives you a constellation of 8 points, which in turn will give you 3 bits of information. So by changing the antennas and the frequencies that you transmit from, you have the different information bits being conveyed. And you can calculate the spectral efficiency, so how many bits per symbol you can transmit for this approach. In our approach, so we're based on, so this is worked together with our radar team in our radar lab. And this is a setup. So the setup basically involves, essentially we're using a radar RF system on chip platform that's been developed in our radar group, which doesn't have MIMO capability, but it can transmit on different different frequencies and different polarizations. And we use these indices to basically convey information. So this is our setup. This is our radar transmitter and receiver. This is our emulated target. And here we have a communication receiver that is controlled by this RF system on chip that's been developed in our radar group. And we use an LFM waveform, so linear frequency modulated waveform, which is basically a waveform that the frequency increases or decreases with time. So a linear chirp, and that's a known waveform for radar sensing. As I said, the indices we are considering to convey information is the center frequency of the LFM, the bandwidth that the LFM spans, and the polarization that we transmit on. So without going into too much detail in the math, on the math and the details of the transmission, we're able to show some flexible trade-offs between the radar performance and the communication performance. So here are the size of our constellations. We can transmit with 11 different bandwidths over 20 different center frequencies, and we have 3 polarization options: vertical, horizontal, or both horizontal and vertical. So these, if you do the math, will give you about 9 bits per symbol. And a key parameter here, and here's an example of different frequencies being transmitted over the air. A key parameter here is the pulse duration of the radar. So different pulse durations and different pulse repetition frequencies obviously will allow many more transmissions of these bits, of these symbols per in time, right? So the smaller pulse duration, the higher the pulse repetition frequency, the more the data rate. However, the smaller the pulse duration, the less integration gain you have for your radar processing. And here's a direct trade-off. So first we plot here the received radar SNR with increasing pulse duration of the radar. And over here, this graph over here shows us the achievable throughput. So the throughput we achieve in this over-the-air transmission. And we compare here a radar-only case. So the green line is a radar-only case where we don't have any communications, no information is being modulated on the LFM waveform, compared to the case where we actually modulate information. So the green one is our benchmark, the blue one is the DFRC waveform. And we show the, as I said, the radar signal SNR and the throughput. And as you can see, as we increase the pulse duration, we have an increase in the radar SNR, so a better radar performance, with a trade-off of a reduced throughput in our communication. And through the radar SNR, we can also calculate the Kramer-Rao lower bound, so essentially the bound on the error estimate on our range. And here you have a direct trade-off between the CRLB and throughput, again, as we increase the pulse duration. Obviously, a high CRLB is bad for radar, so good radar performance is at this end of the spectrum. Good communication performance is at this end of this graph. And again, you can see an explicit trade-off, which is tunable based on this parameter for the example we have in the lab. One thing you can observe probably is the throughput is here measured in kilobits per second, so it's rather limited, and that's a limitation, one of the known limitations of the radar-centric approaches. So we've done some extensions of this setup to try to incorporate more bits per symbol, and also a higher throughput by further reducing the pulse duration. So with a different set of parameters, achieving 10 bits per symbols, we wanted to see how the throughput would change. So here's the throughput with the communication SNR as we reduce the pulse interval. And this is how then we can achieve some, let's say, decent megabits per second rate. And again, this new trade-off, where here we show directly the maximum throughput, so the communication metric, against the radar SNR, so the radar metric, and also the CRLB for the radar range. And again, you can see a flexible throughput as we increase, a flexible trade-off. As we increase the communication throughput, we have losses in the SNR. As we increase the communication throughput, we have a higher estimation error, right? In this elementary example. There's a few things you can do to improve the trade-off, so make the trade-off more benign, sacrifice less radar performance for better throughput, such as integrating multiple radar pulses. This is something we didn't do, or simply, increasing the power, the transmit power of the radar system. But I think this is plenty of research that could be done in this radar-centric approach. Now, as I said, one thing the radar-centric approach has is this limitation. Inevitably, you'll be limited in terms of the communication rate that you can achieve because the radar waveform is not tuned, is not designed to convey information. So weighted optimizations is one way of doing joint DFRC signaling, which has basically gives you, as I said, the flexibility to go from full radar performance to full communication performance. You can flexibly use the resources, time, frequency, power, and so on. And you can move on from high data rates to high radar reliability and all the way in between, and also accommodate these new waveforms and new signaling to become hardware informed and hardware friendly, so friendly to lower specification hardware implementation. And we'll see some examples in a minute. Sorry about this. So here's an example weighted optimization. So here we have the scenario again, a radar-based, dual functional base station, DFRC base station, trying to talk to a number of users while detecting a target. And the communication model is this guy over here. So the receive signal, the communication channel, the transmit signal, that's what we want to design, plus noise. So anything that lives in H times X aside of the information signaling can be considered as multi-user interference, so interference between these transmissions. And that's the metric that we use for communications. And using that, we can have this weighted trade-off design, where essentially we minimize the interference power, so the power of this guy right here, a weighted sum of that with the distance of our transmit signal to a known radar waveform. So once we have a radar waveform, once we design a radar waveform that's good, that gives us a certain radar performance, we want to design a waveform that's close enough to the radar-only waveform, but also minimizes the communication interference. For example, here we have a power budget, so a constraint on the transmit power of this signal. You can have many different variations of this. Another variation is with per antenna power constraints. You can have constant modulus constraints or any other constraints that you want, and make this hardware friendly and hardware informed. You can see this is a weighted optimization, and the key parameter here is rho. So for a high power of rho, this guy becomes significant. If you imagine rho equals, so rho goes from 0 to 1. So if rho is 1, this guy goes away. So you have a communication only optimization. If rho is 0, this guy goes away, and you have a radar only optimization. For rho between 0 and 1, you have a weighted optimization, which gives different priority to comms and radar. Some representative results. So on the communication performance, so this is theoretical algorithmic work. So measuring the symbol error rate with transmit SNR. Our benchmark here is a communication only system without interference, and this is what you achieve in terms of symbol error rate. A number of benchmarks, so some closed form techniques for DFRC that can achieve zero interference and a good radar waveform. And this is what you achieve with the weighted optimization. So well within 1 or 2 dB from the ideal communication only performance. So the communication performance of the DFRC, this weighted optimization waveform, is within 1 or 2 dB of the communication only performance. And this is the beam pattern for the radar operation. So we have 2 cases, one an omnidirectional waveform, which we typically use for detection. And the blue line is the ideal radar waveform. The green and yellow lines are for the cases of this weighted optimization for different power constraints. And then the red line is a directional waveform, which you typically use to track targets. So here we assume 3 targets in these different angles. And the blue line here is what you can achieve with this weighted optimization. I should mention that we have rho equals 0.2, so basically a priority towards the radar operation. And also worth noting that even though our priority is towards radar, we achieve this close match to a communication only performance. So the explicit trade-off in these 2 scenarios, so one for target detection with the omnidirectional design. Here you have the probability of detection, a classical radar metric, versus the achievable rate for the communication system, bits per hertz per user, the units over here. And the blue line shows the case for 8 users. We have 16 antennas in this setup. And you can see that this full-fledged trade-off where from the radar only performance, so with rho equals 0, all the way to the communication only performance. The communication priority performance. One thing to note is that even for the full radar performance, you have a non-zero communication rate, bits per hertz per user. For the communication priority performance, you have some sort of radar detection, some biased radar detection. So it's not a random detection, right? So one point is this. And the second point, as I said, where before you had either radar only or communication only performance, now you have a flexible trade-off between the two systems. And this trade-off becomes more benign as you increase your degrees of freedom, or equivalently reduce the number of users for a fixed number of antennas, or increase number of antennas for a fixed number of users. You'll see this trade-off become more benign, where you sacrifice, let's say, less radar performance to achieve a good communication rate. A similar trade-off for the directional design, angle tracking. Now our performance metric is estimation error, so MSC. So larger numbers of estimation error means worse radar performance. And you can see again, as I increase my data rate, I see also an increase in the estimation error of my radar operation. And again, this trade-off becomes better and better as I increase my degrees of freedom. So I hope it's clear here that we now are able, through this co-design of the signaling, we're now able to achieve a flexible trade-off between communications and sensing. And also that we're able to achieve, even when we prioritize one of the two systems, we still have a certain performance for the other system. And we've recently tried to demonstrate this in our lab, again, to prove to ourselves that this is not just a theory, not a theoretical concept, but we can actually, this works over the air. And here's another setup where we have, this is now our communication lab. We have an antenna array emulating a MIMO access point, 2 communication users emulated by receive antennas. And here we have, let's say, an apparatus where we are trying to measure a beam pattern. So our aim here is to communicate to these 2 users while also forming a beam towards a direction where we assume there's a target that we want to detect. And we're able to see in the lab communication constellations and the theoretical beam pattern, and also measure that beam pattern through this antenna over here. And as you can see, for high weighting factors, you have comms priority, so you have very nice clean constellation, but very little on the beam pattern. As you go towards radar only, you have a clear radar beam pattern, which something like 6 dB, which is the best, I guess, you can achieve with 6 antennas over here, but a very messy communication constellation. And as I said, we've been able to measure these by moving this around in the lab. We've been able to measure the signal strength at different angles and observe the forming of this beam pattern, and also measure the bit error rate, so the communication performance a bit more systematically, where again, we've observed this trade-off that as we increase radar priority, we suffer in the communication performance. So this has been a weighted optimization case where this is what we call the radar-centric weighted optimization, where our aim was to optimize a communication metric while at the same time approximating a good radar waveform. You can do better than that by actually taking into account a bottom line radar metric. So not just trying to approximate a radar waveform, but actually optimize the bottom line radar metric that you're interested in. And here's a simple optimization, a more recent example from this paper, where essentially we minimize the radar Kramer-Rao bound directly instead of the proximity to some radar waveform, subject to communication SNR and power constraints. Again, you can adjust this trade-off by tuning, let's say, this communication parameter, the requirement of the SNR. You have a flexible trade-off on the communication performance versus the radar performance. And this is what you achieve in terms of the beam pattern. Again, without going into too much detail, you'll see that you closely approximate the theoretical beam pattern, but the bottom line performance here is the CRB, right? How well I estimate my radar parameter. And here we have the CRB of the angle with increasing SNR. And these 2 guys over here relate to the beam pattern approximation design, so the one that I showed earlier. And this is what you can achieve. The yellow line is what you can achieve when you directly optimize for your bottom line performance metric for 2 different setups with, so again, here we have 16 antennas. In this more interesting case, we have a closely symmetric channel where we have 14 communication users and one target. So close to symmetrical, let's say, channel where we use all our degrees of freedom. And in this case, you can see instead of approximating a waveform by optimizing the bottom line metric directly, you can achieve something like 3 to 4 dB gain in the SNR from the benchmark performance, right? Where you optimize, minimize proximity to a good radar waveform. Now, another opportunity you have once you start, designing the waveform from the start is to take into account hardware perfections and making this hardware efficient. And here's an example where we tried to incorporate hardware elements in the design and reduce the hardware footprint. So it's probably clear by now that on one hand, you want to increase your degrees of freedom. So increase, let's say, the number of antennas for this dual functional base station to be able to accommodate many users and forming good beams towards potential targets. While at the same time, you want to constrain your hardware, your power consumption, your hardware complexity, and so on. So a natural approach borrowed from the communication only literature is to employ a hybrid analog digital precoding. And here's an architecture here where you have a larger dimension analog processing, smaller dimension baseband processing. To save a bit of time, I'll go directly to the design. So FRF relates to the RF part, so the analog part. FBB relates to the baseband part. And here we optimize these two precoders in a weighted optimization where on one hand we have the approximation of a good communication-only waveform. On the other side, we have a good radar-only waveform. And we have our usual power constraint and some constraints that relate to the analog beamformer, for example, being constant modulus or having finite precision in terms of its angles, and so on. Again, I won't go into too much detail because I'll need the time for the rest of the topics, but some indicative results. Here we're able to simulate a scenario with 128 antennas, transmitting only with 6 RF chains, serving 6 users, and detecting 3 targets. And here we have our rate, communication rate with SNR. Our benchmark is this red line, which is the communication only precoding fully digital, so 128 RF chains just for this case. And this is what you can achieve for this hybrid approach, dual functional approach. As you increase the weighting factor, we call it eta here. So eta, a high weighting factor, gives priority to the communications. And this is the best you can do in terms of hybrid communication precoding. And here's the energy efficiency. So we wanted to measure how well we're doing in terms of essentially the hardware footprint. The energy efficiency is defined as the communication rate over the power consumption, which obviously is a function of the precoders we design, and also the number of RF chains, the RF chain consumption, and so on. And once you now take energy efficiency as your metric, this trade-off is flipped. So you have these hybrid techniques having a much better power efficiency compared to the fully digital approach, communication-only approach, right? So here we're able to provide both functionalities and with a better efficiency than a fully digital communication approach. And this is how our beam pattern looks like. So 3 targets. This is the ideal radar beam pattern. And the observation here is you have these increasing side lobes once you start relaxing the radar constraint. So once you start increasing the communication priority, you're still able to point to the 3 directions you want, but with increased side lobes, which will inevitably affect the radar performance. So moving on quite fast, I'd like to highlight this unique, as I said, security issues that relate to DFRC. So the fact now that you have a radar probing waveform that at the same time carries information to communication users makes it possible for a radar target to eavesdrop. And a radar target can be a friendly node, but it also can be a non-cooperative node, let's say a non-cooperative car in a vehicular communication scenario, or in a military scenario, an enemy aircraft or a malicious UAV. And now you're giving the opportunity by encoding information in the radar probing waveform for that target to eavesdrop. And that's a unique thing, for this DFRC technology. Thankfully, there's a lot of technologies that you can borrow from physical layer security for communications only, such as secure beamforming, artificial noise, and so on. One thing I forgot to say is that even if you encrypt the information on higher layer, the transmission itself, the fact that you're transmitting, can be useful information to the radar target. And that's why you need physical layer security approaches here. So an interesting trade-off that you have in this scenario relates to the radar link. So on one hand side, you want to be able to point energy towards the radar, towards the target. So you want to illuminate the target, so point signal energy towards the direction of the target. But at the same time and at the same direction, you want to limit the useful signal power that goes towards the target. So on one hand side, you want to maximize your radar SNR, so point a lot of power towards the target so that your echo has significant radar capability, significant radar SNR, while at the same time limiting the eavesdropping SNR of the target. And that is typically subject to quality constraints, quality of service constraints for the communication users, such as the SNR of these legitimate users. So this link over here gives you a unique and challenging scenario with some clashing, let's say, objectives. On the other hand side, the sensing capability of radar gives you unique opportunities also in providing communication security. So classical physical layer security approaches benefit from knowing something about the eavesdropper, either spanning from the direction of the eavesdropper or the channel of the eavesdropper or the SNR achievable by the eavesdropper. And these are typically difficult to get. And here the radar functionality, the sensing functionality, gives you an opportunity to actually extract that information, at least in terms of directions of eavesdroppers or link quality of eavesdroppers and so on, or path loss towards the direction of the eavesdropper and so on. So it gives you here also an opportunity to inform these physical layer security approaches, such as secure beamforming, where you want to steer the nulls or jamming and so on. And here's an example scenario. Again, I'll try to avoid the math just to save a bit of time. We've taken, so here's the same scenario, dual functional base station communicating to users, detecting a target while providing secrecy against the target eavesdropping. We've taken an artificial noise approach where the transmit signal is this guy over here, X, what we want to optimize. And it has a structure of the information signal pre-coded by matrix W. And we have this artificial noise over here. Then the covariance of X, which is important for designing the radar beam pattern, is given by the sum of the covariance of the pre-coding and the noise. And then you can formulate the SNR of your communication users as a function of this W, essentially my transmit signal. You can formulate the SNR achieved at the eavesdropper, again, a function of the precoder and the artificial noise. And we use the worst case secrecy rate here. So the worst, let's say, difference between the communication rate to these users minus the eavesdropping rate of the target. Perhaps I won't go into too much detail here, but the example optimization is where we minimize the radar eavesdropping SNR. Sorry, I'm getting a bit of noise, if I can ask you to mute. So we minimize the radar, the eavesdropping SNR, subject to a PSLR of the radar beam pattern. So having a good radar beam pattern that points to the direction of the target with low side lobes, and this is the constraint over here. And assuming some sort of uncertainty of the target location, we want the main beam of our radar beam to be wide enough so that it captures the uncertainty interval. So we don't know exactly where the target is, but we know it should be within this interval. So to make the transmission robust, we employ these main beam region over here. Obviously, once you have this uncertainty, it means you have a wider beam, and it means that you need to guarantee security throughout all that beam, right? So that your security constraints become more demanding. And here we also have the SNR constraints for the users, power budget, and some classical constraints relating to the covariance of the precoder. And this can be solved by known techniques, fractional programming to deal with this guy, and semi-definite relaxation. Some, again, indicative results. So here's how the radar beam pattern looks like. So the dashed line relates to when we know exactly the direction of the target, and we just need to track the target from a narrow beam towards the direction. And here's what you have once you have uncertainty. So you need to widen the beam, so you're able to track a range of angles over here. And that will in turn give you a lower peak to side lobe ratio. And here's the direct trade-off between the secrecy rate this time and the radar performance measured as peak to side lobe ratio. A number of lines here, I won't go into the detail, but the main picture is that you can go all the way from communication secrecy priority to the radar beam pattern priority, and all the way in between, just like we saw in our previous examples. So going one step ahead in further improving security here, we wanted to explore the concept of constructive and destructive interference. And that's a technique that we've been working in my team for the past decade or so. And constructive interference means any interference that pushes your received signal away from decision threshold of the constellation. So here's an example of BPSK. This is the decision threshold. Constructive is any interference, so the green shaded area here, that pushes your signal away from the decision threshold. Destructive is anything that pushes it towards the decision threshold. So that has an impact on how well essentially you can decode information, essentially what tolerance to noise you have, so essentially what SNR you can achieve. As I said, there's many works in the area that have shown significant gains in terms of energy efficiency, orders of magnitude gains compared to classical precoding that I don't have the time to go through here. But the one thing that's important is the mathematical formulation that comes from the geometry. So if this is a PSK constellation, this is an example of QPSK. Constructive region is this green shaded area where the distance from the decision thresholds is increased. And you can come up with explicit mathematical constraints for constructive interference by first phase shifting the general constellation point so that it's on the real axis. And by looking at the trigonometry here, the geometry, you can come up with this kind of constraint. And here you have the imaginary part of this phase rotated received signal, the real part of this signal, the angle over here that relates to the order of the constellation. And gamma here is an SNR parameter that basically tells you gamma is over here. So if I increase gamma, I have further distance from the decision thresholds. So that essentially translates to a higher SNR. Lower gamma translates to lower SNRs. So this, you can employ classical approaches, replace SNR constraints with this kind of constraints, and now you have constructive interference precoding. And here's an example where we employ this in this secrecy DFRC scenario, again, the same scenario. And here we want to use constructive interference to benefit the signals of the legitimate users, and destructive interference to harm the eavesdropping capability of the target. So looking again at the same constellation, we want the legitimate user signals to lie in the green area, the constructive area of the constellation. We want the received signal of the target to lie in the destructive area, so anywhere outside the green shaded area. Again, an optimization-based approach where we maximize the minimum radar SNR, so to optimize radar performance, while at the same time, here's the power budget, and at the same time, we're satisfying some communication SNR threshold, so gamma here is the SNR, with constructive interference, so this will take care of this green shaded area. And at the same time, we have destructive interference for the radar eavesdropping, so that will make sure your signal falls inside these orange areas, let's say. So exploiting the concept of constructive and destructive interference. And this is what the constellations look like. So first we have the approach where we also only exploit constructive interference. Here we have a KPSK constellation and an 8PSK. So this is what the users receive. So the user receives the blue DOS here, assuming that we have transmitted 1 + j, for example, here. And the radar receives anything along, let's say, a unit circle here. We normalize the received signal power for the radar eavesdropper, the target eavesdropper. And this is what happens again with 8 PSK. So the constructive interference is now in this more constrained region. And this is what you can achieve by exploiting both constructive and destructive. And the difference here is that the target received signal never goes in the area of the actual transmitted signal constellation, right? So you have a better secrecy performance. And two indicative results, the radar beam pattern, again, depending on the degrees of freedom, we are able to approximate a good radar beam pattern and provide a good radar performance, while at the same time, provide a good secrecy. So this is a symbol error rate for the communication users, different designs, and for the radar eavesdropping capability. And here you can see a symbol error rate of 0.75 for the target. So for QPSK means basically random guessing of the constellation point. A final thing, I hope I have 5 more minutes to discuss about a use case of DFRC. I want to discuss about a scenario where the communication is served from sensing, so a sensing assisted communication scenario. And here's an example that relates to vehicle communications. So typically in establishing and maintaining a communication link, we have the base station needs to form beams and track with its beams the movement of the communication user. And typically this involves a feedback loop, an iterative process, where the base station first forms a beam, then the communication user measures the quality of the beam, the quality of the link, and feeds back stuff like either the signal to noise ratio explicitly or a preferred beam index. So which of these two, for example, beams I want my base station to transmit. And you can refine further the beams, so make the beams narrower, and that will involve further iterations and so on and so forth. And you have dedicated resources in your frame. So if this is let's say a subframe, you have resources for this beam training, where you have this iterative process and the feedback, and the rest you use for data transmission. So the more time you spend forming a narrower beam, the better sum rate you can achieve within this data transmission, but the higher the overhead you have in establishing the link. So there's an interesting trade-off in terms of the radar beam width. Now, there's particular opportunities here to exploit DFRC signaling, because you can exploit the radar echoes instead of feedback from the user, where essentially you have a DFRC signal that conveys information, downlink information to the vehicular users, and exploits the echoes from these vehicles to form beams and make sure it tracks the communication users as they move along. And this has critical gains. First of all, you don't need explicit resources for channel estimation. You don't need feedback from the users. That means you avoid stuff like feedback errors or quantization errors that come along with this feedback operation. And that also means the whole downlink frame through DFRC signaling can be used for tracking and beam steering. And that has significant gains in the match filtering gain of the radar processing and essentially the beam steering. And here's an example scenario where we have a roadside unit, an access point, tracking communication user. So here we exploit the radar echoes to detect angles of interest where we want to point our beam, and a simple prediction mechanism, so Kalman filtering, to predict where we need to point the next beam. So we use a state transition model that includes all the relevant radar parameters, angle of arrival, distance, velocity, cross-section that relates to path loss, and so on. This is the radar measurement model, and by simple match filtering, you can estimate stuff about this car over here, which is your communication users, one of which is the angle that you need to point your beam. And by using a simple prediction mechanism, you can find out what's the next beam you will need to point to. And here we have a fundamental comparison between this dual functional approach. You can do the same prediction with a communications only approach, you through feedback and so on, which is the other benchmark that we use here. And we have another benchmark, which is again a communication-only approach that relies on the communication user selecting between a pair of preferred beams and feeding back information to the base station for this beam training. And here we have we measure the rate as basically if we assume the base station is at this position and the car moves along the direction of the base station. And you can see with the communication-only approaches, so this purple line, we have with this beam pair tracking, we have an increasing rate until at some point the angle changes so fast that it falls outside these two beams, and you can no longer track the communication users, so the rate drops significantly. The communication-only performance using prediction, you can maintain some performance here, but it suffers by the limited resources that you can dedicate here. So you cannot form, very narrow beams. While in the radar approach, you can form narrow beams and your rate keeps increasing as you move closer to the base station. And you obviously maintain a good link with the best performance out of the three. So I hope this made clear, the use of this sensing assisted approach. And I hope from our discussion, it's already clear that designing new waveforms for communications and radar, incorporating these two functionalities in a single transmission is spectrally energy and hardware efficient. But beyond that, you can design explicit trade-offs. You can design new synergies with sensing assisted communications. And I hope I also managed to highlight some unique security challenges that arise with this scenario. I'd also like to acknowledge the projects that have funded part of this research, a national and a European project. And finally, just to leave you with this final slide, just to basically talk about how I see this going forward. So most of the stuff I've been talking about is making a dual functional base station serve two operations, communications and sensing. There's plenty of work, I think, that needs to go into further exploring this, new metrics, new approaches, making this hardware efficient, energy efficient, and so on. There's plenty more research, I think, in establishing other radar-assisted communication scenarios. Even in the vehicular scenarios, there's plenty more to do. In the previous work, we assumed one vehicle, simple trajectory, but what happens when you have many vehicles to track, complex trajectories, and so on. There's plenty more, again, to do in terms of security FRC. Many physical layer communications only approaches that you can explore to provide security for DFRC. Many opportunities in, again, exploiting the radar functionality to assist with the communication security. And moving towards this, let's say, joint infrastructure, where you have the cellular infrastructure not only doing communications, but doing this dual functionality. One needs to also consider multi-cell and multi-transmitter topologies, where you need to consider interference between different DFRC cells, multi-user communications, multi-cell communications, multi-static sensing, and so on and so forth. So plenty of open research in the area. I think I'll stop here. In the slides, I include some of the references of some works from our team in terms of overviews, coexistence scenarios, dual functional, hardware efficient scenarios, security, vehicular applications, and the recent one on the experimental work. And with that, I think I'll close here, and I'd be happy to take any questions if we have time.
Okay, thank you very much, Christos, for the wonderful talk. And I think we have time for 2 quick questions. So there's a question asked by Lu Wang. So Dr. Wang, can you please unmute yourself and ask the question?
Okay, thank you. Can you hear me?
Yeah, we can hear you.
Yeah. Thank you, Professor. And I want, since I'm a beginner, so I'm also sure about my question, but I still want to ask you. The first one is, in your work, hardware efficient joint radar and communication, there's a work about hardware efficient. In this work, I saw your formulation is a trade-off between communication and sensing. Here, I'm not so clear about why it is hardware efficient. Can you give an explanation about the hardware efficient here?
So, the quick response is that in that formulation, we split our processing into the analog and digital domain. Perhaps I went a bit quickly through this. So splitting this allows you to exploit a large number of antennas while using only a limited number of RF chains. And this is a classical technique. Hybrid precoding is a classical technique that's used in the communication-only literature. So you have a high-dimensional analog processing, typically implemented by phase shifters and so on, and only a few actual RF chains that implement your baseband processing. So in this bit of work, we borrowed this architecture from the communication-only literature to reduce essentially the number of RF chains that you need to use for a DFRC transmission.
Okay, thank you. And my second question is, because you have introduced a lot of work, and in different works you use different metrics for radar sensing. So can you give a brief conclusion about them, and which metric is suitable for which kind of scenario or which kind of problem?
So there's plenty of communication metrics. There's plenty radar metrics that relate to different operations of sensing and radar. So like communications, you have sum rates, SNR, symbol error rate, and so on. Similarly, in the radar literature, you have many of these metrics depending on the operation of the radar. So when you're detecting a target, you have probability of detection, false alarm, and so on. When you're estimating a target, you have the mean square error, the estimation error, Kramer-Rao lower bound, and many others. There's many in the literature. What I hope I conveyed, the main idea I wanted to convey is that you can actually, instead of trying to approximate waveforms, once you employ the bottom line metrics, you have the opportunity to optimize the bottom line performance much better than when you're trying to approximate a good radar waveform. But to answer your question, there's plenty of metrics that you can use from the literature.
Okay. Thank you very much.
No problem.
Okay, so I think we have time for a very quick question. So this is a question from Yiming Ho, and so he's asking about the spectrum. So Yiming, can you please unmute yourself?
All right, so can you and everybody hear me? So I'm Yiming, and so I feel so honored to attend this very inspiring webinar. So my question is related to the spectrum. So people talking about sub-terahertz, terahertz, very promising to be used for the future 6G or beyond communications. So when doing the sensing stuff, I mean, particularly for the radar communications, possibly you will have very strong dependency on the environment, either indoor and outdoor. So could Professor comment on the millimeter wave and terahertz frequency band to be used for the radar communication, and also possibly related to some the radar propagation channels, since usually you would have really tough constraint on the SNR when using the radar, since it's going and backwards, right? So sometimes you even don't have any return feedback from the radar communication. So thank you very much.
Okay, thank you for that question. I mean, none of my work really assumed a certain, let's say, frequency band. It's all kind of baseband, development. The comment I can make about the move to higher frequencies and terahertz, I mean, obviously you have gains in the communication performance with larger bandwidths. You can push more data. Also, you can get performance gains in the sensing. because you can achieve better resilience in better resolution in, for example, range detection with higher bandwidths. As you said, a challenge is path loss. So all these will be much related to the application you want to use. So millimeter wave radars are already used in cars for park assist, so short range, let's say, detection. And with, like for communications, with the advanced signal processing, you can probably extend these applications to a number of other scenarios. But definitely a lot open problems, a lot to do in this area.
All right, thank you very much, Professor.
Okay, so I think that'll be enough for questions. And let's thank Christos again for your wonderful presentation. And if anyone has any further questions, please, you can contact Christos directly using the email, or you can contact me, because lots of works have been done by me, actually. Okay,
absolutely.
So thanks again, Christos. I think we can move forward to our next speaker. Okay, so let me share the screen again. Okay, so we are very honored to have our second speaker, Professor Wei Yu, in this ISAC webinar series. And Professor Yu is now a full professor at the University of Toronto, Canada. And we all know that he has made a great contribution and has very strong leadership in information theory and wireless communication. So Professor Yu was the president of the IEEE Information Theory Society in 2021 and has served on its BOG since 2015. And he was an IEEE ComSoc distinguished lecturer. He has served as area editor, associate editor, and editor for several IEEE transactions and journals. And he was also on the technical program committee for several IEEE conferences like ISIT, ICC, and GlobeCom. So Professor Wei Yu has received numerous awards, including the prestigious IEEE Communication Society Award, Marconi Prize, and several Best Paper Awards from the IEEE SPS. So as far as what I know, Professor Yu has recently won another 2 SPS awards. So in 2021. And of course, Professor Yu is a fellow of the IEEE and a fellow of the Canadian Academy of Engineering. So Professor Yu, we are looking forward to your presentation on active sensing for communication by learning. So Professor Yu, please, can you share your screen?
Okay, thank you for the kind introduction. So let me share my screen. So the title of my talk is Active Sensing for Communications by Learning. So this is joint work with my former and current students and postdocs, Fua Sharabi, Julian Chen, Tao Jiang, and Wei Cui. We're from the University of Toronto. So I'm glad to be part of this integrated sensing and communications workshop or seminar series. So let's go back to see, why do we want to integrate sensing and communications? I believe the strongest motivation is the integrated spectra. Millimeter wave communications, so terahertz, used to be used for sensing applications, but now that's part of 5G wireless standards and likely to be part of 6G as well. So as a result, we have integrated transceiver hardware. We have hardware both capable of doing sensing and communications, and they can potentially share the same waveform. And most importantly, we have applications that demand both sensing and communication capabilities at the same time. So this is why we want to integrate sensing and communication capabilities in future system design. But if you look at most classical communication systems today, I argue that they already have both sensing and communication capabilities. So for example, we do sensing in terms of we do channel estimation before any data transmission can occur. And further, if you look at the classical communication system design, we always embrace kind of sort of separation principle. So for example, we have a separation of source coding and channel coding. Now, of course, you can do joint source channel coding, source and channel coding, but vast majority of practical systems actually separate source channel, source coding, data compression, and channel coding, that is data transmission. Now, if you focus on the channel coding part of the system design, we almost always separate the channel estimation part from the data transmission part. Now, of course, you can do blind channel estimation, but most systems decide to embrace a separation principle. And if you look at the data transmission component, we almost always separate coding and modulation, right? So these separation principles make sense from an engineering perspective, and they're often also supported by information theoretical principles. So in this talk, I'm not going to talk about joint sensing and communications, so to speak, but rather we're going to just focus on sensing and to talk about sensing for communications. And a particular focus of this talk is to look at the role of machine learning in optimizing sensing strategies. It turns out if you just focus on sensing problems, it's already a very interesting problem with where we can see the role of machine learning for future design of sensing systems. So this is what this talk is going to be about. So let's start with a motivating example. So let's consider a massive MIMO millimeter wave system. So here we have a base station equipped with many antennas, and they're serving many users at the same time in the same frequency. So this massive MIMO millimeter system is important for enhanced mobile broadband, and this is a sort of a standard setup for 5G systems. Now, in order to transmit at a high throughput, we need to estimate the channel. But most massive MIMO systems today are not designed as a fully digital beamforming system, meaning that they don't have a full-blown RF chain for each antenna, but rather they do this hybrid beamforming strategy where you design an analog beamformer, then you sample the channel in some low-dimensional space. So this is called analog beamforming, and this is called hybrid beamforming. So one of the key challenges for designing millimeter system is how do we estimate the channel? How do we estimate this high dimensional channel with only low dimensional observations? Okay, so if we have a limited number of RF chains, how do we find the channel direction? And this is called the initial beam alignment problem for millimeter wave system. So let's set up this problem and look at a very simple example of such a system. We have a single user equipment, single user transmitting a pilot signal for the base station, and base station has the task of designing the beamformer for that user. So to do that, he has to estimate the channel. Okay, so let's assume that we have a very simple channel model, where the channel consists of a single path with the angle of arrival theta and a fading coefficient alpha. Now, the challenging part is that although the base station has multiple antennas, it doesn't have a separate RF chain for each antenna. Rather, it has a single RF chain. So it has to look at the channel through a particular direction. And this direction is the beamforming direction, WT, here. So the question is, how should we design this WT in order to estimate the channel? And further, we can potentially design this WT in several stages. Okay, so because of this RF chain limitation, the base station must sense the channel through this analog beamformer. So we're going to design this analog beamformer in an intelligent fashion. And further, we can do this in multiple stages. And you see that this initial alignment problem is really a sequential decision problem in the sense that at any given time, so you consider this channel sensing stage, sensing process happening in multiple stages. And each stage, what you want to do is to look at what the channel is in a particular direction. Then based on the received observation, you can design the direction where you should look in the next stage, according to the previous observations. And you can do this over multiple stages. And at the end, after you have done this over the tall stages, then you can find the angle of arrival for this channel and find the estimated angle of arrival. You see that even for this simple problem, this optimization process of how do you optimize where to look is actually a fairly complex mathematical optimization problem. And this is really a high-dimensional sequential decision problem in the sense that we want to sequentially design these observations in the most efficient fashion so that after these finite number of stages, we can figure out where the angle of arrival is. So let's focus on this sequential decision problem and to see how do we design this sensing strategies in the most efficient fashion. So this sequential design of sensing strategy makes sense. Makes sense. So let me give you an example of such a system. Why to motivate why we want to do this sequentially. Suppose we know that the angle of arrival is between 30 to 60 degrees. So what we can do is we can use a bisection approach. Okay, we can bisection. We can design two analog beamformers, one from 30 to 45 degrees, the other for 45 to 60 degrees, and to see where the angle is between these two intervals. So once we figure out where the angle is, then we can further bisect the angle, and then we can do this sequentially to eventually find out where the angle arrival is. So this is a sequence of beamformers we can design, and these are called hierarchical beamforming codebooks. This is designed in this well-known paper. And this allows us to essentially find the angle using sort of log n number of stages. So let's ask the question of whether this sequential design using hierarchical approach is optimal. Right? So it turns out that this sequential design, you can improve this hierarchical design considerably. But before describing our approach, let's just formulate the problem. So what we want to do is to design the next sensing stage, next sensing vector in an intelligent fashion. But we're going to design this next sensing stage based on previous observations. But this previous observation sort of grows as the number of sensing stages, increase. So what we want is we want something to capture what the observation is so far. So it turns out that if you want to just estimate the angle arrival, then a sufficient statistics for estimating this angle arrival is actually the posterior distribution of this angle. So what we're really trying to do for this in this problem is to map this posterior distribution into the next sensing vector. Okay. So now after the tall stages, after the many stages, then you can finally find the you can estimate the angle based on the final posterior. Okay. So our problem really is the following. We want to find the best estimate of the angle arrival. We want to minimize the MSE of the angle over these two mapping functions. One is to map the posterior of the angle so far to the next sensing vector. And the other mapping is to map the final posterior distribution to the estimated angle. Okay. Now you see that these mapping functions actually are high-dimensional mappings. So if you want to solve this problem directly, it's actually quite a challenging problem. So this part of the message of this talk is that if you use a hierarchical beamforming, if you restrict these beamformers to be in one of these codebooks, one of the beamform vectors in the codebooks, this is actually not the optimal design. A much better design is to use a codebook-free adaptive beamforming to remove the constraint that the beamformer has to be in the codebook and use a deep learning approach to intelligently design these sensing vectors. Okay, to convince you that the codebook-free approach is better, let's first look at a motivating example. So let's assume just a single stage, designing beamformer in one stage. And for simplicity, let's assume that the channel fading coefficient is known. So we ask the question, given a prior distribution of the angle arrival, how do we design the sensing vector to minimize the angle arrival mean square error in the next stage? Now this problem, if you restrict yourself to a single stage, can actually be written down mathematically. So what you can do is you can write down what the posterior distribution of the angle is, given the observation, given one single observation. And this can be written down mathematically like this. Then you can find the best MSE estimation as the expected value of the theta, expected value of the phi, given the observations. Okay, so this can all be written down. So then you can write down what the mean square error is. Mean square error is that this is my estimated angle minus the true angle, take a square, then integrate over the posterior distribution. So the point is that if you just look at the single stage, this is actually a mathematical optimization problem. We can explicitly write down, and where the optimizing variable is which direction to look. So this is the W tau here. you see that this W tau enters this objective function through multiple integrals. There's an integral here, and there are two integrals here. So this whole objective function is quite complex to evaluate. But nevertheless, this is a problem that you can write down. Okay, so how do we go about solving this problem? So let's just take a simple approach and to do a coordinate descent. Okay, so we want to solve this mathematical optimization problem. We can just coordinate descent to find what the optimal WT is. So here's an example. So suppose our posterior distribution is this, between 30 to 60 degrees. If you use coordinate descent, you will find that the optimal sensing vector, sensing filter, will look like this, is the blue curve here. Okay, so it's not intuitive. Why should it look at this direction? But this turned out to be the best direction. But the problem of using coordinate descent is that it's actually mathematically very complicated. In fact, if you integrate, if you try to evaluate this objective function and to do this coordinate descent, it takes several days to derive this sensing vector in our computer. Okay, so this is a highly complex mathematical problem to solve. Now, if you use a codebook-based approach, the computation complexity can be significantly improved. That is, instead of designing over an arbitrary WT, you restrict yourself to these sort of bisection WTs. Okay, so you take WT to be one of these sensing vectors, one of these beamforming vectors in this codebook. Now, so if you do that, the computational complexity can be significantly improved. On the other hand, the achieved mean square error is much worse. In fact, it's much worse. It's like 18 dBs worse than the optimal solution. So hierarchical codebook is by no means optimal, but solving this mathematical problem optimally is computationally complex. So this is where deep learning comes in. So what we're going to do here is to propose a codebook-free beamforming. So we want to not restrict ourselves to this codebook-based design, but we want to improve the complexity of solving this mathematical optimization problem. So what we do is that we take a deep learning approach. We use a DNN, use a deep learning, a deep neural network to map the posterior distribution directly to the optimized solution. Okay. Then we train this deep neural network through many realizations of the sample. Okay. So it turns out this can achieve almost the optimal performance of the exhaustive search of the coordinate descent, while having the complexity much lower than mathematical optimization. It only takes a few minutes to train a DNN to converge to the same as MSE as the coordinate descent. Right, so this is really the motivation for performing deep learning here. And here's how we implement this deep learning module. So in this deep learning module, we take the posterior distribution as the input for the DNN and produce the beamformer, the observation sensing vector as the output. And we also have the power constraint P as the input, and also the number of stage, the stage index as the input to the DNN. Okay, and the DNN is implemented using a fully connected architecture. So how do we train this DNN? We actually do this over multiple stages. So we concatenate these DNN one after another. Then we train the entire DNN as a very deep neural network. But we tie the weights of this neural network across the stages. And we use backpropagation to stochastic gradient descent, backpropagation to train the parameters of this deep neural network. Okay, so the optimal goal is to recover the AOA. So the loss function is the MSE of the estimated angle. So this approach is very effective. Let me show you how well this does. Now, to implement this, we need the posterior distribution as the input to the neural network. So we have to compute this posterior distribution. And this is where the most complexity lies, because computing posterior distribution requires integration. So we have to use a discretization step to compute this posterior distribution. So assume that you have the posterior distribution, then you can implement this deep neural network. But there's one more caveat here. We not only have to estimate the angle, we also have to estimate the gain of the channel, estimate the fading coefficient. So if the K-40 fading coefficient is known, then we can directly implement this neural network approach. But if the fading coefficient is not known, then we had to find some way to keep track of this fading coefficient. So what we can do is we can estimate this fading coefficient, then feed this big fading coefficient as part of the computation of posterior before we feed that posterior to the deep neural network. Okay. And this estimation of the channel coefficients is actually not trivial, because suppose you use the MMSE estimator of the fading coefficient, this will work pretty well, but the complexity is quite high, because you need to keep track of all the past observations in order to estimate the fading coefficient, so that the observation sequence, historical observation actually grow over time. Another way of estimating fading coefficient is to use a Kalman filter. So what we can do is, in order to reduce the complexity, we can assume that the fading coefficient is a Gaussian random variable with certain mean and variance. Then we use a Kalman filter to keep track of its mean and variance. So this also works fairly well, and it actually works almost as well as the MMSE estimator, but with lower complexity. All right, so let me show you how well this system works. So here is the implementation detail of this neural network. We use a fully connected architecture with 4 layers. And let's assume that the angle of arrival come from -60 to 60 degrees, and the fading coefficient is a random vector. We have 128 antennas at the base station. So here are some numerical results. Our baseline are the compressive sensing approach with fixed beamforming. So this is ONP for finding the angle of arrival for the channel. And the 2 hierarchical beamforming approaches, one in this original paper using a bisection, and the other using this posterior matching approach in this paper. So the posterior matching works better than hierarchical beamforming approach using bisection. So this is the red curve here. So this red curve is posterior matching, assuming that the channel coefficient alpha is known. Now, if you assume the channel coefficient alpha is known, our proposed DNN can actually perform much better. So this solid curve is the proposed DNN, assuming also known channel. You see that we have a 5 dB gain, almost about 4 or 5 dB gain in terms of the SNR required to get a target AOA estimation error target. So this solid curve is assuming that the alpha is known, but if the alpha is not known, we have to keep track of the alpha using either MMSE approach or the Kalman filter approach. You see that we have a loss if we don't know the alpha, but even if the alpha is not known, we can do almost as well as the previous state of art, which assumes that the alpha is known. So we see that this DNN approach is very effective in terms of solving of this complex optimization problem. So let's step back a little bit and to talk about really the role of machine learning in sensing and communications, or more generally, the role of machine learning in optimization in general. So traditional optimization is all about efficient search through an optimization landscape. In fact, the Holy Grail of optimization is to transform a problem into a convex form. But there's really no universal theory of how to best transform the optimization landscape. What we have seen here as an example is that machine learning now allows us to have a data-driven approach to optimization. So what we have done is we essentially have moved the complexity from the optimization step to the neural network training process. And once trained, the neural network can directly map the problem parameter to the optimized solution. So if you think of what mathematical algorithm is, a mathematical algorithm is basically a mapping from a problem instance to an optimized solution. So if you see many instances of this problem, you can potentially train a neural network to mimic the same mapping. So when in the testing stage, then when a new problem comes in, then you can directly map to the optimized solution. So in other words, this task of optimization is turning into pattern matching. And the pattern matching is much faster, potentially, for a complex optimization problem. So another way to think about it is that the neural network is now a universal model with large number of trainable parameters that can model any kind of algorithm. So one of the key to the success of using machine learning or using neural network to solve optimization problem is that you ought to match the structure of the neural network to the problem structure. And this is really the key to success. So if we reflect a little bit on how we use machine learning to solve this initial alignment problem, we see that if we just use a fully connected neural network on every stage, we can already outperform the state of art. So this is very good news. But using a fully connected neural network is probably not the best thing to do. You can potentially further improve this performance of this machine learning approach if you explore the problem structure. You see that this fully connected neural network maps the posterior distribution to the sensing vector. But the complexity of computing the posterior distribution is high. And when you have multiple paths, for example, in the system, and the computation of posterior is actually impossible to do. So in the second half of the talk, let me ask the following question. Can we avoid the computation of the posterior distribution in order to save the complexity? That's the first question. And second is, can we further improve the performance by matching the neural network architecture to the problem structure? Okay. So it turns out that the answer to both questions are yes. And we're going to show that if we design a specific neural network for this problem, we can actually get even better performance. So let's think about active sensing problem in general to see what active sensing problems are. So the active sensing problem is about sequential query of the environment in order to find an optimized solution. So what we do is we sense the environment, and in a series of measurements, and based on the received observation, we can adjust the way that we sense the environment. Okay, and after multiple stages of the sensing, then we find the optimal solution according to the received observation. And this type of sequential active learning problem naturally arises in many inference, sensing, and control settings. For example, for tree search, for sequential design experiments, multi-arm bandits is another example of this active sensing problem. Now, for these problems, the analytic solutions are generally not available, and the numerical solutions are generally computationally complex, and they are very hard to obtain. So really, we're asking is that what is the best machine learning model for finding the optimal sequential sensing strategy efficiently? Okay, can we design a machine learning model for this, specifically for the sensing application? Now, this sensing application can be, sensing problem can be mathematically formulated, just as we have done for the millimeter wave initial alignment problem. That is, suppose we have an environment parameterized by this parameter theta. So what we're doing is we're observing this environment, which is a function of the sensing vector WT and the environment theta. Okay, so and the system potentially have additional stochastic parameters. Let's call that U of T. So we design these sensing vector and take the observations. And then based on these multiple observations, then we design the next sensing vector. Okay. And then finally, based on the entire history of the observations, we find the optimal sensing estimate. So one of the key problems of this is how do we design the next sensing vector W of T plus 1 based on the previous observations? Now you see that a key problem here is that this observation vector, its dimension actually grow over time, over the multiple stages. So if you have T stages, this observation Y of 1 to T gets larger and larger as we progress for the sensing. Now in the previous application of previous solution to the millimeter wave sensing problem, we see that we can summarize the previous observation by using sufficient statistics, which is the posterior distribution of the theta. But in general, it's difficult to compute this posterior distribution. So it would be ideal if we can design a neural network to automatically to discover what the sufficient statistics is. Okay, so this is really our motivation for designing these for solving this general active sensing problem. So here is our strategy. So what we do is that instead of directing, so let me go back it a bit. So here, in this problem, we can estimate the we have a final estimate of theta. So this is one possible problem formulation for this active sensing. We can actually have a slightly more general problem formulation where we not only, we don't necessarily want to directly estimate theta, but rather we want to design an action variable, control variable, which is a function of the observation and to achieve some objective. Okay, so we can maximize some objective. So we just want to design this V. So again, in this design, we want to design the sensing vector in the next stage as a function of the previous observations. And finally, we want to design the control action here. So what we want to do is to propose a unified deep neural network, a deep learning framework to handle this general formulation over the multiple stages. Now, again, the key difficulty for designing neural network is the fact that these observations grow over time. So we want a way of automatically discover what this state information is. We want to discover what this sufficient statistic is. Okay, so we want to tackle the problem that the dimension of the historical observation increase as the time index increase. So it's desirable to abstract the useful information about this historical observation into a state variable and to discover the state variable. That's what we want to do. And once the state variable is known, then we can use a deep neural network to map the state into the optimized WT, optimized sensing vector. So the key question is really how to generate the state variable from the function of historical observations. So this is where this LSTM comes in. So what we propose to do is to use a long-term short-term memory architecture to capture the state. And this LSTM network is widely used for natural language processing to keep track of arbitrary long-term dependencies in the input sequence. So this is a sequential decision problem. So we need to understand the long-term dependencies between these sequence of decisions. So this is the mathematical formulation of the LSTM cell. So let me draw this in a picture to show you what the LSTM look like. So here's the LSTM cell. And the key variables are the cell state. So there's CT, it's called cell state. And we also have a hidden state called SFT. And the cell state and this cell state CT and the hidden state ST are connected to each other in an intricate fashion. So it has a forgetting gate here, has input gate, and also has output gate. So this is one single LSTM cell. And this LSTM cell then will be concatenated with the LSTM cell in the next stage. So here, our observation of the environment is concatenated with the state as input to the LSTM cell. Then, in order to design the next sensing vector, we use a DNN to map the state to the next sensing vector. And this sensing vector will result in the observation. This observation will be concatenated into next LSTM cell. Okay, so this is what LSTM look like. The fact is that we're going to train this LSTM so that it will discover what's the best formulation of the state. So in a sense, it's discovering the sufficient statistics in a problem. So how do we train this DNN? So what we do is we concatenate this LSTM cells over the multiple stages. So for example, we have 10 stages. We have this 10 LSTM cells and they're concatenated with each other. Then we consider this whole concatenated LSTM as a very deep neural network. And our objective is either estimation of the channel parameter or a control action to maximize some utility function. Then we can use stochastic gradient descent to train the parameters of this LSTM as well as this DNN for mapping the state to the sensing vector, as well as this final DNN to map the state to the control action or the estimated parameter. Okay. And further, we tie the parameters of these LSTM across the multiple stages so that they're easier to train. Okay, so this is our approach. And this can be applied to both the estimation of the state as well as the optimization of the control actions. So let's now apply this structure to our millimeter wave beam alignment problem. So again, we have a channel consists of now potentially multiple paths. So we have an uplink sensing stage. We want to design the sensing vector WT through a single RF channel in order to understand what the channel is. Then based on the channel, we're going to want to design the downlink beamformer. Okay. So we can formulate the problem as that of minimizing the mean square error of estimating the angle of arrival. So this is one possible problem formulation. Or we can formulate the problem as to design the beamforming vector in the downlink beamforming vector in order to maximize the beamforming gain. Okay, so this is an example of maximizing utility function as a function of the observed channel in order to maximize the beamforming gain. Now, both of these problems are in the form of this generic active sensing problem discussed earlier. So we can use the proposed LSTM approach for optimizing the mapping from the channel observation to the next sensing vector, as well as the final mapping to the desired beamformer or to the estimate of the channel. So here are some implementation details. We use an LSTM cell with 512 states. Then there are two DNNs, one for mapping to the sensing vector, the other is the final DNN for mapping to the final control action, or the of the estimate of the observation. And these are traditionally fully connected DNNs, but this LSTM cell is really the key part of this program that allows us to keep track of the longitudinal dependency across the multiple observations. So here's how well this works. So the two light blue curve are what we had done previously, the DNN approach with either known alpha, this is the solid curve with known alpha, or with unknown alpha, but using a common filter to track the alpha. So this purple curve, the purple solid curve, is this new LSTM approach for estimating this angle arrival. So here, this purple curve assumes that we don't know alpha, but we use LSTM to automatically discover what the sufficient statistics of the channel of the estimation process is. Now you see that assuming the channel is known, we outperform the previous DNN approach where we estimate the alpha by another 5 dB, right? So in this proposed approach, we assume that the channel is not known, and previously we had to use a common filter to track the channel. So it turns out this proposed approach with unknown alpha does almost as well as the DNN approach with known alpha. In other words, we get the estimation alpha for free. Now, this approach can be applied not only to coherent setting, but also to non-coherent setting. So for example, let's assume that we here the single RF chain does not have does not estimate the angle, only estimate the magnitude of the observation. Then we can train the same neural network in the same way. Then we can get very respectable results, even assuming that the observation is non-coherent. So now let's take a look at what this LSTM-based deep neural network is actually doing. So here, what I'm plotting here is the posterior distribution of the AOA over the multiple stages, okay, and the corresponding designed sensing vector. So this is t equal to 0, t equal to 1, 2, 3, for example. So here we're assuming that the angle comes from -60 degree to 60 degree, and the true angle is at 9.96 degree. Okay, so this is just one example. At the beginning, the posterior distribution of the angle is arbitrary. So we don't know where they are. So we have uniform distribution across the -60 to 60. And then the corresponding designed sensing vector is plotted here. So really, we're just doing a fishing expedition of trying to figure out where the sensing vector is. So we have sort of no idea where that is. So we do this, we designed this very broad sensing vector. But based on this sensing vector, we already have some idea. So if you compute the posterior distribution, then we have some idea where this angle is. You see, the true angle is actually here. So our posterior is not very accurate. But based on this posterior, we can already design another sensing vector to sort of fine tune the direction so that we can get a better idea of what the AOA is. And based on these two sensing vectors, now we have a better idea of where the angle arrival is. Then we design another corresponding sensing vector. We get even better idea where the angle is. Then we design another sensing vector. So eventually the sensing vector will converge to sort of have a sharp peak on where the true angle is. True angle is 9.96. And the posterior distribution will converge very sharply to where this angle arrival is. You see that this neural network is trained in arbitrary fashion, right? So we're not telling it what the state description is, but it's doing very sensible things. So the design sensing vector and the designed posterior can be easily interpreted. So this is really an interpretable kind of deep neural network that we have designed. So now this approach can be easily generalized to multiple different settings. So here's another setting where we assume the sensing vector satisfy the constant modulated constraints. For example, we can only have phase control in these sensing vectors. So it turns out that this DNN approach does very well also, and it's have a similar performance as compared to a previous approach with known alpha. So we get this tracking of alpha for free. Right. So this is another example. So here's a multi-path example where we have multiple paths. So previous path in this example, we assume that we have only a single path. If a multiple path, sort of none of the previous benchmarks actually works with multiple path, and the best you can do in the previous literature is just use the ONP. But with the neural network approach, we can get significantly better MSE performance as compared to the previous capacitor sensing-based approach. Here's another example where we do not look at the estimation error as a metric, but rather we look at downlink beamformer as the metric. So here we have a 3-path system, and each of these angles come from -60 degrees to 60 degrees. And we look at the downlink beamformer design using this LSTM approach. And the ultimate performance limit is this blue curve, which assumes a perfect CSI. Then if you use the traditional approach of using ONP to do a channel estimation, followed by maximum ratio combining, this is what you have. This is the curve this is the curve you have. Now, if you use random sensing vectors, you can already do better than explicit channel estimation. So this is the green curve, but the best performance is obtained when you actually design these sensing vectors. So this red curve is if you design the sensing vector using DNN. And this purple curve is if you design these sensing vectors in an active fashion. So this red curve is if you design the sensing vector over the multiple stages, but they're fixed, they're not a function of the previous observations. But if you take this active sensing approach, this is when you get the best performance. Okay. All right, so this is one example of an active sensing and why active sensing is an interesting problem, and why deep neural network can be useful for solving this problem. So in the final couple minutes of this talk, I'm going to talk about the application to intelligent reflective surface, and to see that active sensing also has a role to play there. So here's another application where active sensing is interesting. Intelligent surface is a device that allows a transmitter to direct its electromagnetic radiation toward the intended receiver by reflecting its electromagnetic radiation in a specific fashion. So this is most useful when the direct link from the transmitter to receiver is blocked. So what you can do is you can adjust the elements of this RS in a way such that the electromagnetic radiation is directed to the intended receiver. Now, in order to implement this RS system, you need to understand the channel first. Okay, so typically what you do is you transmit a pilot signal from the receiver to the transmitter so that the transmitter learns about the channel. Then based on channel reciprocity, then you design the beamformer at the RS so that the beamforming can be maximized from the transmitter to receiver. Now, in the channel sensing stage, you see, you can also change the RS coefficients, right? So this can actually be formulated as an active sensing problem in the sense that you can have the receiver transmit multiple pilot signals. Then based on the received pilot signal that you have received so far, you can adjust this RS coefficient in the sensing stage so that you can get better and better look at the channel. So you see that in this RS channel estimation problem, this is also an active sensing problem in the sense that this sensing, you're really measuring a high dimensional channel based on low dimensional observation at the transmitter, but you can change the direction in which this channel is being sensed. Right? So you can formulate a problem of maximizing the overall beamforming gain in the downlink as a function of how you do the sensing. That is, in every sensing stage, I'm going to change this RS in the specific direction so that my channel estimation error my channel estimation gets better and better. So this is why this adaptive channel sensing problem is actually an active learning problem, because you have a controller that's capable of controlling this RS coefficient, so you can do this in the sensing stage as well as in the downlink transmission stage. So you can use the same LSTM framework to do this sensing, to do the active sensing problem. And here is implementation of this LSTM network. We again use LSTM cells with 512 states. And the channel model here is a Rician channel, which means that it has a strong line of sight component. So here's an RS coefficient configuration of 8 by 8 rectangular array. So here is the performance of this active sensing. So again, this blue curve is the perfect CSI case. Now the traditional approach is to first do a channel to estimate the channel, then you match the phase of the channel in order to maximize the beamforming gain. So this is the performance you will get, the beamforming gain as a function of the number of sensing stages. So this is the traditional channel estimation based approach. Now a significant performance improvement can already be obtained if you bypass channel estimation and directly design the beamformer based on the received pilot. So this is the approach that's proposed in one of our previous work. So, but in that work, we assume that the sensing vector at the RS is random, is set randomly. If you set the sensing vectors in, to be adapted to the channel, you can do much better. So the red curve and the purple curve are these adaptive channel sensing design. This red curve is if the sensing vectors are adapted to the channel realization. And this purple curve is when the sensing vector is not only being adapted to the channel environment, but also be active in a sequential fashion. That is, based on the received observation, I actively design the next sensing vector and do this sequentially so that I can get a better look at the channel. You see that this active sensing actually performs the best. We get something like 1 or 2 dB performance gain as compared to a non-active but adaptive approach. Okay, so let me conclude this talk. So sensing will be an integral part of all future wireless communication system design. There's no question about this. And this is why we're in this integrated sensing and communications seminar series. So the point of this talk is that active sensing is an important problem in practice, and it's an interesting problem theoretically. We saw that deep learning can tackle complex mathematical optimization problems more efficiently than traditional optimization approaches. So we saw that deep learning gives a viable data-driven methodology for designing active sensing strategies. We give 2 examples. One is the initial alignment problem for millimeter wave communications, and the other is the sensing matrix design for reflection alignment in RS systems. In both cases, we see that active sensing is highly beneficial. And the main point of how to apply deep learning for sensing of communication applications are really the following points. We want to make sure that the learning objective should match the application objective. That's very important. And we also see that it's beneficial to bypass the explicit channel modeling and explicit channel estimation, really to design the sensing strategy or designing the parameter you want to estimate directly based on the received pilots. And this is beneficial. And the most important lesson is really that you should design the neural network architecture to match the problem structure. So here we have a sequential problem. That's why this long short-term memory structure is ideally suited for this application. Okay, so this talk is based on these 2 papers. I just want to put in the reference here, as well as, again, to acknowledge my students and postdocs who are the main contributors to this work. And both of them are available on our archive. Okay, so thank you very much. This concludes my presentation.
Okay, thanks, Professor Yu, for the very wonderful talk. And we have received some questions. So I think the first question is from Fernando Petraza on the back propagation. So Fernando, can you please unmute yourself and ask?
Hi, yes, so thank you very much for the wonderful presentation. I'm curious about how to actually train the network that maps the internal state from the LSTM to the beamforming vectors. Is it like in the figure there was like a plot, a cloud that was labeled with environment? Like, is that like the dynamics of that environment, are they provided to the network so that it can back propagate through it? Or otherwise, like, which kind of target signal you try to minimize there?
Yes. So we have to provide we have to assume that the statistics of the channel realizations are known. So we run many examples of this channel. So eventually the neural network will learn what the statistics of the channel is and to design its beamforming vectors according to the channel statistics. So for sure we need to provide the statistics in the training process. So we generate many samples of this environment in the training process. This is how we generate lots of data.
Yes, but even with many samples, my question is usually, like, in order to learn the weights for that L layer DNN, you would need to take the derivative of the final output with respect to this hidden state of the LSTM, and for that, like, you need to also know, in this case, for example, the derivative of this, or gradient of this YT with respect to WT. So yeah, is the network able to calculate those gradients in order to be trained, or?
Yeah, so we take a mini batch approach. We take a particular weights, so we do many realization in the environment. Then it gives a particular objective function, the loss function. Then you can back propagate to see that if you change the weights of this neural network, how much better would you do with respect to this mini batch? So you have to generate many samples to summarize what the effect of the neural network weights on the final objective function is.
Okay, yeah, okay, I think I get it. Thank you very much.
Great, thank you.
Okay, so we have a second question from Peter Tioka. So he's not traveling, so cannot speak. So I'll ask on behalf of him. So he asked, is the proposed active sensing robust when the environments are different between the training and the testing stages?
Yeah, so this is a good question. So what you want to do is to train this over lots of different environments to make sure that the neural network has seen many examples of the environment in order to be robust. So this is a typical thing that you would do for neural network training. For speech recognition, for example, you want to make sure that you've seen many different kinds of speakers in order to be able to recognize speeches from many speakers. So this is a typical difficulty for using a neural network approach. But let me say that if you try to do robust optimization, the traditional optimization framework, that's even more difficult, because then you would need some kind of statistical model of the variations of the channel. And typically that would lead to very difficult mathematical optimization problems, difficult to solve. So it's, for robust optimization, it's actually much easier to just generate many different samples of the environment in order to make sure that your final solution is robust.
Okay, thanks, Professor Yu. So actually myself has, so I have two questions about this work and some potential future extensions. So the first question is that actually many sensing problems, the behavior of the object to be sensed may follow some specific models. So for example, recently, Christos and I, we have done quite a lot of works on integrated sensing communication for like vehicular communication, vehicular networks. So the vehicles may have some specific kinematic models depending on the traffic conditions and the roadway geometry. So how can we leverage this model in your proposed framework?
Yeah, that's a good question. In the sense that we already leverage this model, and we designed this, we assume that this channel is of a particular form. It has have a fading coefficient, it has a mathematical model that describes with the angle of arrival how that relate to the channel. So if you have a vehicle-to-vehicle communication scenario, you will have a similar model, either line of sight model, or there should maybe finite number of reflections for another vehicle. So in a sense that we already designed this, assuming this model. If you want to be completely model agnostic, then the amount of training needed to design the final solution will be considerably more difficult. So in the sense that this is already a model-driven approach. I mean, it's a data-driven approach, but accounting for the model, that's what it is.
I think Christos has something to ask. So please, Christos.
No, just a comment on this very topic that you asked, Fan. I think it would be interesting to maybe see how you can model the evolution of channel H based on the mobility of the user. And I think that would be the connection from what Fan says to what you are showing here, Wei. And maybe the geometry is difficult, and maybe learning has a role there to play.
That's right. So these are two separate things. So here we assume the channel is fixed, and we're looking at active learning. We're trying to, we're looking at the channel multiple times in order to figure out what the channel is. Now, if the channel changes over time, for example, this angle arrival has a time evolution over time, then this is a separate model that we need to track the changing of the angle of arrival or changing of the fading coefficient. So that's an additional layer of tracking that we will have to do. So you can potentially also use sort of an RSTM approach to do this. And in fact, I think when I saw one conference paper that does exactly this.
Okay, thank you very much, Professor Yu. I think there's another audience. So Sild, can you please unmute yourself?
Yeah, hi. I also have one question, please. It's actually the same question as someone else asked earlier about the backpropagation. So this is actually quite a question for me as well. So I just wanted to ask, would it be possible for you to actually maybe provide a GitHub code for this so we can actually see what's happening? This is very difficult to understand in terms of what's happening in the network.
Yeah, we'd be happy to. We'd be happy to. Yes.
Okay, that would be really helpful. Thank you very much, and thanks for the interesting presentation.
Feel free to send me an email. I typically post that on my own website.
Okay, so I have a final question again for myself. So I'm very interested about. So you have mentioned about bypassing this channel estimation stage, so you can directly map the let's see the observation or the sensing signals to a communication strategy. Let's see. So here you map the sensing results to let's see a beamformer, right? So actually, in many let's see integrated sensing and communication scenario, we're also thinking about to bypassing the channel estimation stage, but instead we're not using the conventional channel estimation, but we're using a radar to sense the, let's see, sense the environment. So this will be rather different. So your sensor results will be rather different from the let's see the conventional channel estimation. So conventionally we use design a communication strategy directly based on the communication channel estimated results. But if we are going to use, let's see, so the so-called active sensing, so radar is actually doing this active sensing. So you transmit the sensor signal and it reflected back to the radar, and then based on that results, how can we design, let's see, a communication strategy by using this framework? So I'm not sure if I make this clear.
So bypassing channel estimation has huge benefit. There's no question about that. I'm happy to report that. So here's an example. If you split the channel, estimate the channel, you do very poorly as compared to a case that you bypass channel estimation. And the reason for that is that the traditional channel estimation process assumes a particular model of the channel, has certain number of parameters, then you try to estimate those parameters. But not all parameters are of equal importance. Some of the parameters are not important in terms of designing a subsequent beamforming strategy. So there's no way for you to know a priori which parameters are more important than the others. That's why if you can directly map the received signal to the communication strategy, you get a huge performance gain already. You're asking, I think what you're asking is, how do you apply this to the radar setting? So,
yeah, so how can we use the radar sensed results to facilitate, the communication strategy design?
Yeah, so to me, there's no difference between radar sensing and the channel estimation. I mean, at the end of the day, you're sensing a particular channel. If you use this particular radar waveform to sensing the channel, you get certain output, and that output will be a function of the channel parameters. So if you use a different sequence to sense the channel, you also get some information on the channel. So at the end of the day, it's about how many different dimensions in the channel that you're exploring, and how well that you know the channel as a result. So you can use whatever sensing strategy that you want to employ, and based on the output of the sensing, design a mapping from the output of the sensing stage to the control action, to the actionable thing that you want to design. And that can be typically trained using neural network. So that's what I'm proposing. And some sensing strategy may be more efficient than the others. So that's when the statistical channel comes in. So suppose you already know certain parts of the channel, then you know that you should look at this part of the channel more carefully than the other channels. So that will affect performance. But that's assuming that you have some knowledge of the channel distribution, and you have to take advantage of that.
Yeah.
So you can always design this mapping using a data-driven fashion to get what you wanted to design at the end.
So actually, we're wondering if we're going to use radar sensing, so compared to the conventional channel estimation. So we typically call this so for radar sensing, we typically call this device-free sensing. For channel estimation, we call it device-based sensing because it is cooperative. And for radar sensing, it is non-cooperative. So we wonder if there's some performance, performance gap between these two strategies. So device-based or device-free. So that is actually some open problems that we want to explore. Yeah. So that is one of my comments on this.
I see. I'm not sure what do you mean by device-free. It means so entirely based on base station.
Device-based means that the sensed object actually has, let's say a communication device attached to that object, and device-free means that there's no such communication device on that object.
I see. So just based on reflection from the object.
Yeah, right. Yeah, so we wonder if there should be some performance gap between these two strategies.
Right. Depends on the channel model, depends on the situation, depends on many different things. But in principle, it's possible to do. But then depending on the model of the two, I mean, there's going to be difference between the two models to give you the performance difference.
Yeah, right. Okay, I think that'll be enough for all the questions. And thank you again, Professor Yu, for this very interesting talk. And we hope to see you in our future events. And also, we would love to host you again in our future webinar series.
Thank you very much.